Hello, and welcome to our lesson on exponential functions. In this lesson, we will firstly understand what an exponential function is. Then we will explore the shape and behavior of its graph. And finally, identify various real-world examples where exponential functions are applied. Following this, we will apply our new knowledge to various problems to solidify our comprehension and see these functions in action. So far, we've built a strong foundation by working with quadratic and cubic functions. You are familiar with their respective shapes and how they behave. Quadratic functions form parabolas, while cubic functions create curves that can have one or two turns. Additionally, we've looked at reciprocals and how we plot asymptotes. To begin, let's introduce the general form of an exponential equation. An exponential function can typically be written as y equals a to the power of x, where a is the base, a constant, and x is the exponent, a variable that we change. Let's recall the function x squared that we've looked at before. Here, x was the base and 2 was the exponent. But in exponential functions, we flip the script. The base remains constant, like 2, 5, or 7, and the variable is in the exponent, such as 2 to the power of x or 5 to the power of x. A particularly unique and important base for exponential functions is the constant e. The number e is approximately equal to 2.718 and is similar to the constant pi, in that it frequently appears in various areas of mathematics. Thus, an example of an exponential function using this base would be y equals e to the power of x. Let's explore the exponentially growing function y equals e to the power of x by working through a table of values and plotting its graph. Let's start with a few values. When x equals -2, then y equals e to the power of -2, which approximately equals 0.135. When x equals -1, then y is equal to e to the power of -1, which approximately equals 0.368. We complete the table for x equals 0, x equals 1, and x equals 2. In the same way, using these points, we can sketch the graph of y is equal to e to the power of x. Here's what we'll notice about the graph's shape. The x-axis serves as a horizontal asymptote. This means as x goes toward negative infinity, I to the power of x approaches but never actually reaches 0. And the y-intercept is at 0, 1 because e to the power of 0 is 1. On the right-hand side of the graph, the function increases very rapidly as x becomes large. This rapid increase is characteristic of exponential growth. Conversely, exponential decay, like y is equal to e to the power of negative x, results in a graph that decreases rapidly as x increases. This is reflected over the y-axis, compared to y is equal to e to the power of x. To graph these functions effectively, step 1 is to identify the y-intercept. For simple exponential functions of the form I is equal to a to the power of x, this intercept will always be 0, 1. Step 2, determine if the function represents growth or decay. Growth functions, like y equals e to the power of x, increase to the right, say, while decay functions, like y equals e to the power of -x, decrease. Step 3 is to recognize the horizontal asymptotes. For y equals a to the power of x, the x-axis acts as an asymptote. For more complex functions like y equals ae to the power of x plus b, the asymptote shifts, but can be found by considering the term added at the end. With the intercept, growth or decay behavior, and asymptotes in mind, we can plot the y-intercept, as well as additional points, and draw the steep curve in the correct direction. We must ensure that the function approaches but does not cross the horizontal asymptotes. Finally, let's discuss how to find approximate values on the graph. Suppose we need to find the value of y for x equals 1.5. On y equals e to the power of x, Step 1. Locate x equals 1.5 on the x-axis. Step 2. Move vertically to find the corresponding point on the curve. Step 3. Read the y-coordinate from this point. Using the table approximation for x equals approximately 1.5, then y equals e to the power of 1.5, which equals approximately 4.481. Conversely, if given a y value, locate that value on the y-axis, move horizontally to find the curve, then drop down to read the x-axis value. And there you have it. This is how we understand, graph, and utilize exponential functions. Next, we'll move on to see how these concepts are applied to real-world scenarios. For our first example, let's consider a basic exponential function. Consider the function y equals 2 to the power of x. First, let's create a table of values to understand how this function behaves. Now, if you plot these points on a graph, you'll notice that as x increases, y increases very rapidly. Conversely, as x decreases, going negative, y approaches 0 but never actually touches the x-axis. This gives the graph its characteristic steep upward curve. For our second example, let's look at exponential growth in a real-world context. Imagine a population of bacteria that doubles every hour. If we start with one bacterium, how many bacteria will there be after 5 hours? We can use the exponential function to model this situation. Here, y is equal to 2 to the power of x, where x is the number of hours. For x is equal to 5, y is equal to 2 to the power of 5, which equals 32. So, after 5 hours, there will be 32 bacteria. For our example 3, let us now look at exponential decay. Suppose we have a radioactive substance that decays such that it is reduced by half every hour. If we start with 100 grams, how much will be left after 3 hours? We can model this situation with the function y is equal to 100 multiplied by 1/2 to the power of x, where x is the number of hours. For x equals 3, y is equal to 100 multiplied by 1/2 to the power of 3, such that 100 times 1/8 is equal to 12.5. So, after 3 hours, 12.5 grams of the radioactive substance will be left. Additionally, if we look at the graph, after around 10 hours, there is less than 1 gram of the radioactive substance left. However, it never actually reaches 0 due to the nature of exponential decay. For our fourth and final question, let's consider a financial example involving compound interest. Suppose you invest £1,000 in an account that offers a 5% annual interest rate, which is compounded yearly. How much money will you have after 2 years? We can use the compound interest formula, which is an exponential function where y is equal to the following. Here, p is the principal amount, £1,000, r is the interest rate, 0.05, and t is the time in years. For t equals 2, y is equal to 1,000 multiplied by 1 plus 0.05, comma, to the power of 2, such that y is equal to 1,000 multiplied by 1.1025. And finally, y is equal to 1,102.50. So, after 2 years, you'll have £1,102.50. By working through these examples, you can see how exponential functions are not only a fundamental part of mathematics, but also crucial for understanding and solving real-world problems. In today's lesson, we began by defining an exponential function in the form y is equal to a to the power of x, where a is a constant base and x is the variable exponent. We highlighted the special base e, approximately equal to 2.718, as it frequently appears in various mathematical contexts. We then examined the graph of the exponential function y is equal to e to the power of x. We noted its key characteristics of a horizontal asymptote at y equals 0, a y-intercept at 0, 1, and rapid growth as x increases. Conversely, we discussed exponential decay using the function y is equal to e to the power of negative x, which decreases rapidly and reflects over the y-axis compared to y equals e to the power of x. To effectively graph these functions, we identified crucial points and behaviors, such as the y-intercept, growth or decay direction, and horizontal asymptotes. We also covered how to approximate values on the graph by locating points along the axis and the curve. Finally, we touched on the application of these concepts in real-world scenarios, setting the stage for practical problem solving. Understanding and graphing exponential functions enables us to tackle complex problems related to population growth, radioactive decay, and financial interests, among others. Watch the rest of the GCSE Maths course at Sophos Education.